Mercury stands as the innermost sentinel of our solar system, a small, rocky world locked in a relentless orbit around the Sun. Its surface, scarred and cratered, serves as an open book chronicling the dramatic events that shaped not only this planet, but the entire inner solar system. Unlike Earth, where plate tectonics, weathering, and erosion erase much of the geological history, Mercury preserves the scars of cosmic violence as a testimony to the earliest epochs of planetary formation. When we look closely at Mercury's craters, we are essentially reading pages from a primordial history. Each crater represents a moment frozen in time, the violent collision of an asteroid or comet with the planet's surface. These impacts were far from rare. They were fundamental to the process of planetary evolution. The relentless bombardment from space debris during the first few 100 million years of the solar system sculpted the surfaces of all the terrestrial planets. Mercury's proximity to the Sun meant that it was especially vulnerable to these impacts, experiencing collisions that were often more intense than those on Earth or Mars. The density of craters on Mercury is a key clue to understanding its geological past. Regions densely peppered with craters are among the oldest surfaces in the solar system, dating back over 4 billion years. By contrast, areas with fewer craters suggest more recent resurfacing events, often from volcanic lava flows that flooded ancient basins and plains, erasing older craters beneath fresh rock. This contrast allows scientists to construct a relative timeline of Mercury's geological activity and understand how the planet evolved over time. Among the most fascinating features on Mercury is the Caloris Basin, one of the largest impact basins in the solar system. Spanning roughly 1,550 kilometers across, Caloris is a colossal scar from a cataclysmic event, an impact so powerful it sent shockwaves rippling through the planet's interior and produced chaotic terrain on the opposite side. The sheer size and complexity of Caloris offer insights into the magnitude of forces at play during the solar system's violent youth. By studying the basin's structure, scientists learn how Mercury's crust responded to such an impact, whether it fractured, folded, or rebounded, and how its interior may have softened or flowed in response. Beyond the large impact basins, Mercury's surface is dotted with thousands of smaller craters, each with unique characteristics. The shapes, depths, and ejecta patterns of these craters provide clues about the impacting body's size, velocity, and angle of collision. For example, an impact at a steep angle typically creates a more circular crater with symmetric ejecta, whereas a shallow angle produces elongated craters and asymmetric debris patterns. By mapping these patterns, researchers gain insight into the distribution and trajectories of impactors in the early solar system. Adding further intrigue are the enigmatic hollows, bright, shallow depressions often found inside craters. These features are unlike anything seen elsewhere in the solar system and suggest active geological processes that release volatile substances. The most plausible explanation is that solar radiation causes certain minerals in Mercury's crust to vaporize, leaving behind pits and depressions. This discovery challenges prior assumptions that Mercury, given its extreme heat, would be devoid of volatiles. The presence of hollows hints at complex internal chemistry and surface dynamics that are still not fully understood. Moreover, Mercury's poles harbor another remarkable secret: water ice trapped in permanently shadowed craters. Despite Mercury's blistering daytime temperatures, the steep walls of some polar craters cast permanent shadows where temperatures remain below freezing, creating cold traps where ice can survive for billions of years. The detection of water ice, confirmed by radar and spacecraft observations, reshapes our understanding of volatile delivery and retention on airless bodies. It also opens exciting possibilities for future exploration, as these ice deposits could be a vital resource for human missions venturing closer to the Sun. Studying Mercury's craters also helps refine planetary chronology, the science of dating surfaces based on crater density and distribution. This method, called crater counting, is fundamental to planetary geology. By comparing crater populations on Mercury with those on the Moon and Mars, scientists calibrate the ages of surfaces across the solar system. These comparisons deepen our understanding of the timing of major events, such as the Late Heavy Bombardment, a period marked by a spike in impact activity roughly 3.9 billion years ago. Mercury's crater studies intertwine with the broader question of planetary formation and solar system evolution. The giant impact hypothesis for Mercury's high density, for instance, posits that a massive collision stripped away much of the planet's original mantle, leaving behind a dense, iron-rich core and a thinner silicate shell. The craters on Mercury might hold remnants of this transformative event, revealing details about the nature and timing of such colossal impacts. In addition, Mercury's crater record supports models of planetary migration in the early solar system. The so-called NICE model suggests that the giant outer planets, Jupiter, Saturn, Uranus, and Neptune, shifted their orbits during the solar system's youth, destabilizing the asteroid belt and triggering waves of impacts on the inner planets. Mercury's heavily cratered surface provides crucial evidence for this dynamical upheaval, linking planetary motion to geological history. Exploration missions have been key to unlocking these secrets. NASA's Mariner 10 mission in the 1970s gave us the first close-up glimpses of Mercury, revealing a cratered, moon-like surface. But it was the Messenger mission, launched in 2004 and orbiting Mercury from 2011 to 2015, that transformed our knowledge. Messenger mapped the entire planet in unprecedented detail, analyzed its composition, measured its magnetic field, and identified key surface features such as hollows and polar ice. Building on these achievements, the joint ESA-JAXA Bepi-Colombo mission, launched in 2018 and expected to arrive at Mercury in 2026, carries even more advanced instruments. It promises to map Mercury's surface with higher resolution, study its exosphere and magnetosphere, and probe the planet's internal structure through gravity measurements. The data from Bepi-Colombo will help us understand how Mercury's magnetic field is generated and how its interior cools and contracts over time, all while refining our interpretation of its cratered surface. Beyond pure science, Mercury's craters invite reflection on the nature of change and permanence. They are enduring witnesses to cycles of destruction and renewal, reminders of the cosmic forces that shape worlds over billions of years. The same impacts that create craters also deliver essential ingredients for life, such as water and organic molecules. Thus, Mercury's battered surface is not just a record of violence, but also of the processes that make planets habitable. In the grand tapestry of the cosmos, Mercury's craters connect us to fundamental truths about creation, destruction, and transformation. They bridge the microscopic and the astronomical, the ancient and the present, the simple impact and the complex planet. By studying these scars, we uncover stories that go beyond one small planet, reaching into the history of our solar system and beyond, to distant exoplanets and the universal laws that govern planetary evolution. Mercury's craters are chapters in the cosmic saga, each one a narrative etched in stone, waiting for us to decipher its message. In reading them, we not only learn about Mercury, but about the origins of Earth, the potential for life elsewhere, and our own place in the vast universe. The planet's silent surface speaks volumes to those who listen, offering lessons in resilience, history, and the profound beauty of a world forever marked by the passage of time.